So now I can, I can change this concept of an inverter followed by a pass transistor. Right? This was D, phi, let's say phi bar. You got something here. What was the alternate circuit I said that can be used instead of this? Cascading an inverter by a transmission gate. Yeah? I told you one more circuit which has similar functionality but slightly different configuration. Yeah, buffer with a clock or an enable. It's called a tri-state inverter. I can replace with inverter. Right? Therefore, I can simply replace this structure with this kind of a thing. So here I said this is phi bar, and this will be my D, and this will be my Q. Right? So I will represent this with a symbol like this, inverter and an enable phi, dy. It means phi is connected to the NMOS transistor, phi bar is connected to the PMOS transistor. That's what this symbol means. So now I can replace that flop that I had earlier with such a structure. Okay, D. Then I will, in the feedback path, I could put another tri-state inverter, right? Or I could consider that like a, okay, let's put another tri-state inverter there, not a big deal. So let's say this is phi, then this has to be phi bar, right? Then I can put another tri-state inverter here, which is phi bar, feedback inverter, Q. Okay? And this is QM. Right? So in general, if you look at this Q is what is going to be available to the outside world. In the sense, the next gate's input will be connected to this Q, right? Which means that that node is going to be available as a wire somewhere, right? And any noise on the output, suppose there is a noise on the output, let's say there's a large noise, then this feedback path can potentially get affected. Okay, because remember, this is now trying to hold some data, right, in a feedback mode, and let's say the noise is large enough that it could flip it. Then the state of that flop can potentially flip, right? In order to avoid that, what you do is you isolate this output in the following way. You add another inverter and make Q available here instead of here. Okay, which means now Q is what is going to connect to the next gate, and any noise will affect only this guy. This internal node is not going to be available to the next circuit. I can shield that appropriately, right? Therefore, now any noise on QM is at the output of an inverter as opposed to input of this inverter here. And therefore, the noise will not percolate backwards and affect my functionality. So this is a latch or a flop, right, with isolation. Okay, so let me just show you one more interesting circuit here. Okay. Yeah. Okay. What is this? Look at this latch here. Okay. I'll basically copy paste this here. Okay. So this latch, okay, of course it's been drawn with a pass transmission gate in the beginning. You can always replace that with a tri-state inverter. It doesn't matter. Is this latch a latch with breaking the feedback or overpowering the feedback configuration? Yeah? Okay. Is it true for both logic states? Huh? No. So that's what I'm saying. So you have to tell me this analysis now for if D was 0 and if D was 1, what would happen? So let me replace this with a tri-state inverter. Okay, it may be easier to analyze. This is clock bar. So if this node happened to be, let's say, a 1, okay, that means the feedback path is holding a 1, therefore this is a 0. That means in that condition, if I want to now flip the flop, right, if I want to flip the state, D has to be, I want to make this 1 go to 0. That means D has to be what? No, initially this node X has a 1. I want to make it 0. Therefore, D has to go where? 1. So, D has to go from 0 to 1. Okay, and clock also has to be enabled. Only then it can happen. Now, when that happens, what will happen to this path? There's basically a NMOS transistor here, right? Which is basically not this guy has one NMOS transistor to ground, right? Which is connected to D. And this is now becoming 1. So there is a pull down path like this. Earlier, when the intermediate node was storing a 1, it was being pulled up through which transistor? Through the weak transistor that is shown here. This was the pull up path. So there is going to be a fight between the PMOS of the feedback inverter which is labeled as the weak transistor here, and the pull down of this tri-state inverter, which means it is what kind of, is it breaking feedback or overpowering feedback? Yeah, right. So you have to overpower feedback in this case, right? So therefore this is overpower feedback. Other way, suppose the node X had a 0 and I wanted to make it 1. Then node X had a 0 means it was being pulled down through which guy? It was being pulled down through this path, right? When clock was 1. Now clock goes to 0. I want to sample the data, I want to bring it in. So when clock goes to 0, what happens to the feedback path? It breaks. And therefore now my tri-state inverter is free to write its data unconditionally. So here this is breaking feedback. Why didn't they do it the other way around? Where they said that let us do breaking feedback for the 1 case and overpowering feedback for the 0 case. Exactly. Here note that when there is a fight between this PMOS and this NMOS. It's always easier to make the NMOS stronger with smaller area than the PMOS. If I had done the reverse case, what would have happened is there would have been a fight between the NMOS here and the PMOS of that inverter. Now the tri-state inverter has to win. Therefore, the PMOS has to be sized up significantly. So in order to reduce area, you have to do this only on the, by sizing the PMOS down, right? So you allow the fight to happen between an NMOS pull down and a weak PMOS pull up. That's why you will see this weak PMOS pull up in many places, because it's very easy to make a PMOS weak with small area. Okay? Any questions here? Okay. So now, as I told you, I had this tri-state inverter D with a feedback. Right? This was 5 bar. Question is, do I really need this? With the element that is storing my data or that is going to hold my data is this feedback inverter. Right? If there's a 0 at the input here, the output will be 1. That output will drive the 0, and this feedback will hold it steadily as long as the power supply is on. Right? Therefore, this is known as a static latch. Just like we did static CMOS and dynamic logic in combinational circuits, you also have the corresponding static latches and dynamic latches in sequential circuits. Okay? It turns out that there is a capacitance here, and therefore technically that capacitance can store the value for a short period. Ultimately, if you look at what should happen, each latch needs to hold the data for half a period. The holding needs to happen for half a period. The other half, it's transparent. So there is something driving it. So if you look at very high clock speeds of the order of gigahertz, then the data has to be held only for 1 nanosecond. Right? And technically it is possible to do this with a reasonable capacitance on chip. Right? And therefore you can simply use a tri-state inverter as a dynamic latch. Fine. Okay? So now let us look at this connection, right? I said a tri-state inverter had to be like this. This is D, D, phi, phi bar. Can I swap D and phi? Logically, this is also a valid flop, right? Phi bar, phi, and then this I will call as D. Logically, these two are the same, right? When phi becomes 1, both of them act like an inverter. When phi is 0, both of them don't provide a path to either VDD or ground, thereby tri-stating the output Q. Q will be in high impedance state. But are these two equivalent otherwise? So let us look at what we want from a flop. This is my clock. Data is, so now I'll draw, okay. So this is phi. This is my D, okay. So let's say that my D is changing like this. What should happen to Q after the data has been sampled and is going to be held? So in this case, when phi equal to 1, data is going to, the latch is in what state? It's in transparent state, right? So any change in D will just go through, right? There's no problem there. So if you look at the output here, this is a positive latch. So therefore, Q will simply follow D with an inversion, of course, and some delay. Now let's say D changes here, right? So this is, latch is transparent, latch is opaque. When the latch becomes opaque, any change in D should not reflect in the change in Q, correct? But now, in this configuration, let us say that this Q was basically what? 1. Okay, Q was 1 and my D now went to 0. Okay, I'm looking at this transition here. So if D was 1, then my, no, so what should, oh sorry. This is what should happen, right? Because T has changed here and Q should get inverted in the transparent phase, right? So D was 1 and Q became 0. So this capacitor was discharged to equal to 0, right, out here. Now when D becomes 1, this Q is now going to get connected where? It's going to get connected to this capacitance, right? There is an intermediate capacitance Cx here and this is Cl, which means that this node will now charge share with Cx. You agree with me? What was the state of Cx when the clock went low? Huh? Q has fallen, right? Q has fallen, right? Now at this phase, right, in this period here, my clock PMOS is on, right? And my D has, what has happened to D? It has gone high, thereby turning off this guy. So what is the state of Cx? VDD. right? Vc of 0 minus is VDD. So this Q now, because of this, when my data falls, right, in the opaque state, will now charge share and come to some in between value. In this configuration, any change in D after the clock has shut off will not reflect the change in the output Q, because the clock is actually getting that change right in between. So therefore, this is the only correct configuration for a tri-state inverter, and this is not a correct configuration for the tri-state inverter. So in this configuration, configuration 1, Q will continue to be at 0. Of course, now it depends on what this charge shared value is, right? Whatever this value is, it will go to something between 0 and VDD, right? This will be greater than 0, less than VDD. Depending on where it goes and lands, the following stage may trip or not trip. But that's not a good thing. Okay? Any questions here? Okay. So now we will look at a configuration which is a very interesting configuration from the perspective of clock overlap. Okay, this is going to be my D. This is phi bar phi. This is phi and this is phi bar. QM Q. Okay? So this is just a dynamic flop. Two dynamic latches have been cascaded. That's all we have done. Okay, this is latch L1, this is latch L2. Okay, what kind of a flop is it? Positive edge triggered or negative edge triggered? Yeah, because when clock equal to 0, the data will go through, and therefore this is a negative latch, this is a positive latch. Together you get a positive edge flop, and it's a dynamic flop. Okay, now I'm going to analyze this thing for the clock overlap condition that we discussed earlier. This is my sampling edge now, correct? The rising edge is my sampling edge. So this is phi bar. I'm going to delay phi bar a little bit now, okay, as usual. So this is my overlap. Okay. This is what? 1-1 overlap, and this is 0-0 overlap. Okay. So first let us analyze the 0-0 overlap case. Okay. So what will happen? Can you tell me what transistors will be turned on? Okay, let me label them N1, N2, P1, P2, N3, N4, P3 and P4. Yeah. In my 0-0 overlap condition, which transistors are off? Both phi and phi bar are 0. Yeah? All the NMOS. So N2 and N4 are going to be off. These transistors are basically off. Okay, so maybe let me, because I need the other condition also, so let me make a copy of this. Yeah. Okay. So therefore, I am going to now remove these transistors from the path. Okay. For the 0-0 overlap condition. Fine. So now I want to see if a change in D can percolate all the way to Q or not. Right? So should I even analyze this particular condition? I mean, which of the two transitions should I analyze is my question. Should I analyze D going from 1 to 0, or should I analyze the other case? Let's say D went from 1 to 0 in my 0-0 overlap period. Okay? Or D goes from, let's say 0 to 1. Sorry, let's look at the red case first. D goes from 0 to 1 in my 0-0 overlap case. Can the change in D go to QM first of all? No. Why? Because that NMOS has already cut off. So there is no discharge path available. Therefore, the only condition I have to analyze is this condition, where the data goes from 1 down to 0, thereby there is a pull-up path, right? So QM can therefore now, right? So let me draw this in blue so that there is a pull-up path, right? So therefore, what happens to QM? Let's plot that. QM was initially what? 0, right? At this edge, it's going to sample 0 because D is 1, QM is an inverted value of D. Therefore, it will be 0 here. But now D has switched, right? And it's going to pull QM all the way up, right? With some delay. Correct? I will not go all the way till the edge. Let me draw it till here. So the change has now percolated to QM. Question now is, can it go further from there? No. Why? Because I need to discharge through the NMOS transistor and there is no pull down path here. Right? So on the non-sampling edge, nothing goes through. What is it that did the trick compared to the previous case? So we analyzed an earlier case where there was on the non-sampling edge, the overlap was a problem, and we said you have to make sure that the delay through these gates, take care of the overlap. What is it that is doing the trick here? Or if put it other way, if I were to go back to that static latch or flop and apply the same thing and ensure that the non-sampling edge overlap is not an issue, what should I do? Yeah? Remove the? So there is a very critical thing. You see that in both cases, only the pull-up path is available, both latches. But in order for data to go through, one has to pull up, other has to pull down. Only then data can go through. So there is a logic inversion that is doing the trick here. Earlier, when I used a transmission gate, the transmission gate was conducting for both 0 and 1 logic. What we have done here is, for 0 you are going through the PMOS, for 1 you are going through the NMOS. Right? If for example, if I replace this guy with a circuit like this, right? This is also a dynamic latch, right? And I put another inverter here and make a flop like this, right? Let me call this as phi bar, right? Or so this is phi bar and phi. I cannot do that here. The same thing will not hold, because now for both 0 and 1, these two transmission gates will conduct, and therefore I have a race path available. What is doing the trick is making the 0 conduct only through the NMOS, making the 1 go only through the PMOS, and then there is a logic inversion in between, which is ensuring that these two are complementary to each other. Clear? Okay, so now let's look at the other condition, which is basically on the sampling edge, I want to see what happens. Right? This is phi bar. So 0, 0 overlap, there was no problem. This is my 1, 1 overlap. What are the transistors that are going to conduct? Or what are the transistors that are going to be off in this overlap period? P1 and P3. So I can remove these transistors off. Correct? Now what is the condition that I have to analyze first of all? Okay, before that, tell me, after the overlap period, which latch is in which mode? L1, L2. Right? This is L1 and L2. After the overlap is done, it's a positive latch. It's a positive flop, positive edge triggered flop. Therefore, L1 has to be in opaque mode, and this will be in transparent mode. And this will be in transparent, this will be in opaque. Right? So now, again tell me, if I should analyze the case where D goes from 1 to 0 after the overlap, after the clock falls, or the other way. Which condition should I analyze? 0 to 1. Why? Because if D goes from 1 to 0, there is no pull-up path. Therefore, that's not even going to go through. That change cannot even go through to QM. So forget about Q. Therefore, I can ignore this condition completely. I am going to look at only this particular condition. T going from 0 to 1 in that overlap. Now, this is the difference that you have to be careful about from the previous analysis that we did on the non-sampling edge and the sampling edge. Okay, remember, if D happens to go through, right, because there's a pull down path. There is a pull down path available. Therefore, if D goes to 1, QM will fall to 0. What happens after the overlap is done? Yeah? What is happening in L2 after that? It is transparent. That means any change that has gone through to QM will go straight to Q after that. And therefore, you will have a serious violation. Therefore, QM, if you look at this, will basically happen to be like this, right? And Q, which was actually supposed to sample the edge 0, right? will actually get inverted like this, somewhere in between. Okay, my sampling edge is this. And there is a problem. How do I solve this problem? Yeah? Someone just said it. Hold. Again, hold time condition. Anytime there is a problem on the sampling edge, you have a rescue. It's called the hold time. Impose a condition that my hold time should be greater than the overlap period and I'm done. The flop will work. It is a violation on the non-sampling edge that is going to ruin your circuit. And you should never have a violation on the non-sampling edge. Sampling edge, you can impose this condition. Worst case, let's say you designed it wrong, something happened, you just say, okay, my hold time is larger. It doesn't mean that the circuit is unusable. But if there is a violation on the non-sampling edge, then that's a race condition and it is not even fixable later. You have a big problem. You cannot impose a hold time constraint or a setup time constraint. Okay? So in this case, you just impose the condition of T hold should be greater than T overlap of 0, 0. I mean of 1, 1. I'm sorry. Yeah. Why Q1 becomes why QM? Why Q? Because QM has become 0. And after that, that's what I'm saying. Look at what has happened. After this overlap period, what has happened to L2? My PMOS transistor is back. And both are conducting. It's like an inverter now. It's transparent. That's why you have to very carefully analyze what happens after the overlap period. During the overlap, it's okay sometimes to allow data to go through a little bit. But it depends on what happens after the overlap. If L2 becomes transparent, then you have a problem. Okay? Any questions here? Okay, so what is the setup time of this flop? It is basically just a delay of L1, right? T, not inverter, I'll call it tri-state of L1, right? Whatever delay, as long as you are able to charge that capacitor on QM correctly, your setup is done, right? If you cut it off before that, then you have a problem. What about TCQ? Yeah? Exactly. This is T tri-state L2. Okay? This, by the way, is called a C-squared MOS flop, right? And each state is basically a latch. C-squared MOS latch. Essentially, this is insensitive to clock overlaps. What do I mean? It doesn't mean that both overlaps is not an issue. One overlap is still an issue, but I can alleviate that by imposing a hold time constraint. It's always the other overlap period that's a problem, and this flop is insensitive to that overlap. The non-sampling edge overlap is not an issue. Okay? By the way, I leave it to you to analyze what happens if 5 bar comes early. That could also happen, right? Clock and clock bar, it doesn't mean that clock bar is generated from clock always. Clock and clock bar may be generated separately and then distributed to the entire chip, which means clock bar could come early also. You never know. So you can analyze that condition on your own and so you have to see how that's going to change your analysis. clock to Q now, right? What is clock to Q? Basically, my clock has gone high, which means that L2 has become transparent. It is how long it's going to take to charge Q. QM has already been set up now. QM has already been charged because of the setup time. It's only a question of how long QM takes to go to Q. That is clock to Q. Because when my clock goes high, that means it has sampled the data and L2 has become transparent. Q has to charge. So that is just a delay of L2 under ideal conditions. Okay? Any questions here? General analysis of this clock overlap. It may take some time for you to digest it, go back, look at the other circuits also, analyze what happened and see, and then come back to me later if you have any questions. Okay?